Other addressing mode is the register addressing. So, where the source or destination is one of the CPU registers, like typical example like move R0 comma A, where R0 gets the content of A, then move A comma R7, A gets the content of R7, move A comma R4. So, like that we can make one of the operands, one of the source or destination as the CPU register, like say this instruction move dptr hash to 25 F5 hex. So, this dptr pair will get this value. So, dph will get 25 and dpl will get F5, or we can have this individual registers accessed dpl, dph. So, R5 comma dpl. So, dpl's content will come to R5. So, there should be a number here, say R5, R4 or R3, something like that. The register number is missing, that comma dph. So, that register will get the value of the dph register. So, as I told previously that I cannot have an instruction like move R4 comma R7. So, this is not allowed. Okay. So, this is not allowed. So, if you really want to move the content of current register 7 to register 4, so you have to give the corresponding memory address. So, you can write something like this, that move 4 comma 7. So, essentially what will happen is that the memory location 4 will get the content of memory location 7, and assuming that your memory locations are current register bank is the bank 0, then this will be transferring the content of register 7 to register 4. If you are using some other bank, so appropriately we have to calculate these two memory location addresses, and then we have to put those values. So, this way we can use this addressing, we can use this register addressing for transferring control between the registers, transferring values between the registers. Then we can have direct mode. So, here in the direct mode, so we specify data by 8-bit address. So, usually the addresses are in the range of 30 hex to 7F hex. So, we can write like move A comma 70 hex. So, content of memory location 70 hex, so they will be coming to the A register. So, this is that 30 to 7F memory range that I was talking about. So, this is in the direct mode we can use them. Then move R0 comma 40 hex, copy content of memory location 40 hex to R0. So, this way we can do this thing, like so this one, say move 0D0 hex comma A. So, 0D0, so this happens to be the PSW register. This is the special function address 80, D0 is the special function address for this register PSW. So, there the content of accumulator will go there. So, you put the content of A into the PSW register. Then we can play with R0 to, so then we have got the direct mode. So, in the direct mode, so we can have this instructions like move A comma 4. So, instead of writing registers, so when you are writing like move A comma R4, so it is you can get this it is equivalent to move A comma 4. Then we can have this move 7 comma 2, which is equivalent to move R7 comma R6. Then move A comma 7, so this is correct, but this one we cannot write move A comma R7, so this is not allowed. Then move R2 comma hash 5, so put 5 in R2 and move R2 comma 5, so it puts the content of RAM 5 in R2. So, this we have already discussed. Only thing to note is that this move A comma R7, so this is not allowed in, so R7 cannot be used in the direct addressing mode. You can use this register indirect mode. The address of the source or destination is specified in registers. So, you can say like say PSW, you can say like move PSW hash 0. So, so that sets that usage of register bank 0, and then we are telling that move R0 comma 0x3c. So, R0 gets the value of this 3c, and then at the rate R0 we are putting the value 3. So, what will happen is that since R0 is having this value 3c, so this 3c will be used as the memory address, and then this memory address will be going to this memory address 3c will be getting the content that we mentioned here. So, when we execute this instruction move at the rate R0 comma hash 3, so it will be getting the memory location 3c will get the value 3. So, only the registers R0 and R1 can be used for this purpose. So, you cannot use any other register, like you cannot have an instruction like move @R2 comma #3. So, that is not possible, only R0 and R1, and we have to be careful that R0 and R1 they have been initialized with proper values. So, in this case when we do this, so we are setting R0, first of all we set the bank, then in that bank in the R0 register we are putting this value 3C and then doing this movement. Or you can so that is for internal memory operation. So, internal memory when you are trying to access in indirect mode, so you can do it like this. So, if you are trying to use external memory in indirect mode, then we have to use this DPTR register. Okay. So, this instruction, this pair of instructions, so they will be putting the content or they will get the content of memory location 9000 into the A register. Okay, and 9000 is an external memory location. So, we first of all move the value 9000 to the DPTR register. Okay, so, DPH gets 90, DPL gets 00. So, DPTR pair gets 9000 hex, and then we say the move hex A comma @DPTR. So, it will be accessing the external memory and memory location 9000, from there the content will come to accumulator A. So, move x is not allowed for internal memory access, similarly move is not allowed for external memory access. So, this x, so this will mark that the processor is trying to access the external memory. Then we have got this registered indirect mode, the source and destination address is the sum of the base address and the accumulator. Some accumulator can be used as an index, like say this one. So, DPTR has 4000 hex, move DPTR comma has 4000 hex. So, DPTR gets 4000, then we move A comma 5 and then we say move C A comma @A plus DPTR. So, A's current content is 5. So, this DPTR value will be added to that. So, that way we get the value 4005, and then so that from this external program memory, so we are getting the value into the A register. So, this is useful when you are having some sort of lookup tables. Okay. So, what happens is that this whenever we are having some lookup table, so maybe we have got some function f x, and for different values of x we have got a table. So, this is the x and this is the f x. So, this is 0, 1, 2, 3, so up to some value, say up to 100. We have computed the values and those values are stored in, so these are the different values. So, while writing the program, so instead of writing the code separately, what we do is that we take a portion of memory and then there we write down the values of this function f at various locations. The first location has got the value of function f0, then the next one is at f1, next one is at f2, like that. This is typically useful when you are say for example, doing some filtering operation where these signal samples are multiplied by filter coefficients. So, filter coefficients are fixed, okay, so that are not going to change. So, they can be, the filter coefficients can be stored in this type of lookup table. Now, since these values are not going to change, so in some sense we can say that they are part of code, as the values are not going to change. So, what we do? So, they can be, so in your program that you are writing, so this can be a part of the program. So, after that we have got the main program, but this entire thing can be treated as the program. Now, you need to access the contents of these locations for doing some operation. Now, this particular example that we have here, so what it is doing? So, somehow suppose this is stored from the external memory location 4000 onwards. So, 4000, 4001, like that. So, we are trying to access the fifth value. So, f5, if we are trying to access the location, the value of say f5, then with this 4000 we add 5, so that it comes to this particular address, and then move C A comma @A plus DPTR. So, what this instruction, what it, so with the DPTR the value of A register will be added and the @ is on this whole thing, okay. @ is on A plus DPTR. So, that is the semantics. So, that value becomes 4005. So, memory location 4005's content comes to the accumulator. So, that way you get the content of this location. So, this is very much useful when you have got this type of lookup tables stored as arrays in the external memory, and then you can use it for in your code. Okay. So, for that purpose this has been thought about, and since this microcontrollers are used for embedded applications. So, many times we have got this type of situation. So, maybe we have to have some complex function. So, though it is difficult to compute it every time. So, what is done is that they are computed once only at the design time, and the values are kept as lookup table, and that becomes a part of the code. So, that can be done. So, next let us see another one. So, where it is so we can also have this PC, this base address can be DPTR or the program counter. So, we have seen an example where the base address is DPTR. So, this other one is, so whenever other possibility is that we can have this thing from this with respect to PC, like move a comma hash 5, then 1000 to moves at 1000 to we have got move C a comma at the rate a plus PC. So, a plus PC, so that will be having this memory location 1008. So, that this because this is 1000, and this is after this instruction has been fetched. Okay. So, after this instruction has been fetched, the PC value is 1003. So, with that 1003 this 5 will be added. So, it will become 1008. So, that way we can have this 1008 memory location content available in the A register. So, this move C instruction, it can read internal code memory. So, that way so it can get the value from there. Then the A register, it can be accessed by direct and register mode. So, both direct and register mode can be used. So, these three instructions have same function with different type of code, like so the address of this A register is E5. So, we can have this move A comma 00. So, that is coded as E500. Then move ACC comma 00 hex. So, that is also coded in a different format 8500 E0, and similarly. So, this is move 0E0 comma 0A. So, this is also actually that accumulator. So, E0 is the address of the A register. So, E0 being the address of A register. So, all these are same. Okay. So, you can so this is this instruction and this instruction, they are same, and this is semantically same with this instruction, though the size of the instruction here is 2 byte and here they are 3 bytes, but semantically they are same. Similarly, these three instructions like move C, move A comma R1, then move accumulator comma R1 and move 0E0 hex comma R1. So, they are all same. Okay. So, E0, as we say that E0 is the address of accumulator register. So, there that way it remains, it is same as that one. So, all these instructions they have got the same meaning. Some other special function register like the B register. So, it is always, it can be used in direct mode excepting in the multiplication and division operation. These two instructions it can be used separately. So, this move B comma 00 hex. So, this is the code 8500 F0, then move 0F0 00. So, this is also the same instruction, same meaning, but they can have different formats. Okay. So, all these will be same. The B is coded as F0. So, that F0 comes here. So, here also the same thing. So, two instructions having the same meaning. Then P0 to P3, so they can be used as direct address like move P0 comma A. So, this is so we can have this P0 register is this 80, P0 register's address is 80 hex. So, this is F580, then we can have this instruction which will be, this is also F580, but here 80 is mentioned explicitly. Then we can also have move P0 comma P1, like say so this is P0 is 80 and P1 is 90. So, move P0 comma P1. So, this becomes a 3 byte instruction, we can have something like this. So, these are this P0 to P3. So, we can use them as direct addresses. Then other SFRs like PCON, TMOD, PSW, so they can also be used as used for these movements. So, all special function registers like accumulator, B, pcon, etc., they are accessible by name and direct access, but both of them must be coded in as direct address. So, while writing in the assembly language program, so we are writing them as name or direct address, but while the machine code is generated, so they are coded as direct addresses only. So, that is obvious. Next we look into the immediate addressing, like say move say add a comma 3d hash 3d hex. That means with the a register we want to add the value 3d hex. So, this instruction is a 2 byte instruction, or the first byte is the opcode, and opcode for add a is the 24. So, that is the 24. Then the add a immediate. So, add a immediate is 24, and the immediate value will be proceeding, will be following the opcode. So, that is the 3d. So, this 3d is the immediate data. Then in the direct addressing, so we can have like move R3 comma 0 E8 hex. So, that means the content of memory location 0 E8 hex will come to the register R3. So, this is the this opcode is AB and the address is E, and the address, the value, the address value is E8. So, that will come to this second byte. So, we can have this way the direct addressing. So, this is the instruction format like register addressing. So, this opcode will be there, and there will be 3 bits which will identify the register. So, this move A, so all these instruction, so all these move A type of instruction, they have got the code like say E, and then this these first 5 bits are fixed. Okay. So, this is for the move A, the first 5 bits are fixed, and then the next 3 bits will identify the register R0, R1, R2 up to R7. So, that way this opcode coding is done. Similarly, add A has got the code as again the 5 bits will come, and this will turn out to be 2. So, this last configuration will come where these bits are actually 0 0 1 0. These 4 bits will be 0 0 1 0, and after that we will have 1 1 1 1, because this is R7. Okay. So, that way these 3 bits will correspond to 7, and this 0 0 1 0 1. So, that will be the opcode for add A. So, this way we can have different coding for different instructions, and they have got the so that is so they have got the uniformity. So, this will be in this format. On the other hand, if we have talking about this register indirect addressing, then we know that only 2 registers are allowed, like R0 and R1. Okay. So, we can have I equal to 0 or I equal to 1. So, the 1 bit is sufficient at the end to identify that this is R0 or R1. So, when we say that move A comma at the rate R1, so that is coded as E7. Then similarly, move C A comma at the rate A plus dptr. So, this will be coded as 93. Then this move C A comma at the rate A plus PC. So, that will be coded as 83. So, this way this will be done. Move X at the rate dptr comma A. So, this will be accessing this thing. Okay. Then we have got the relative addressing. So, the relative addressing is one category of like this comes in the context of jump instruction. So, if we see this jump or this JMP instruction in general, so all these jump operations that we have. So, if you look into any processor, the instructions are like some opcode for jump and then the address to where you want to jump. So, typical example, say in 8085 we have sent jump 2000 hex. So, this what it does, it loads the program counter with the value 2000, so that the next instruction executed is the instruction stored at location 2000. So, this jump we can have different type of classification. One classification is from the functionality, which is conditional versus unconditional, conditional jump versus unconditional jump. So, this we have seen, like we have got jump on carry, jump on 0, jump on not 0. So, they are conditional jumps, and we have got unconditional jumps like the JMP instruction. Another classification of this jump can be like this: absolute jump and relative jump. Absolute jump and relative jump. So, what is it? Like say suppose at present we are executing, we are at location memory location 1000, and there I am putting from here I want to go to the location 1500, put a jump instruction there, so that the next instruction executed is the instruction at location 1500. Now, this is fine. So, execution will be fine. So, here what is happening is I am telling specifically that what is the destination address. Okay. Destination address is specified directly. So, you can say that destination specified directly. Another way of doing the same thing is to tell that it is jump by plus 500 locations. So, something like that. So, at present I am at 1000. So, if I say plus 500, so with respect to current location you go forward by 500 locations. So, this means that go forward by 500 locations. Okay. So, when I go forward by 500 locations, so after executing this one or this one, the effect is same. So, it comes to this address only, but the way we are telling it is different. Similarly, you can say jump minus 400, so that you go back to location 600 in the execution. So, that way we can do both forward and backward jumps, and so this type of jumps, so they are known as relative jumps. So, these are actually the relative jumps that we talk about, because these jumps the target address is specified relative to the current address. Okay. Relative to the current address we are telling where do we want to jump. Now, why all these things, why this relative jump is so coming into picture, why is it so maybe so important or at all useful. So, it is like this: suppose I have written a program, and this program has got at there is an instruction like jump 1500 here, where 1500 is somewhere here, and this program is starting at location 0. Now, where if this is my ultimately the computer's physical memory, and if I assume that the program is loaded from memory location 0, if I assume that the program is loaded from memory location 0, then this jump is fine. So, this is loaded here. So, when it comes to this particular instruction, so it executes jump 1500, so it goes to location 1500. But next time, instead of next time you run the program, instead of being loaded from location 0, suppose the program is loaded from location 5000 onwards. The program is loaded from location 5000 onwards. Then what happens is that this jump, so this 1500 address, so this is no more 1500, this is basically 6500. So, again I have to make this correction in this program. So, this should be jump 6500. So, if you are using absolute jump, then every time the program is loaded from a different address, this jump addresses they are to be corrected. Okay. So, but if it is relative jump, so that is not required, because here I am not telling jump 1500, what I am telling is jump by plus 500. That means, with respect to the current location, so you jump forward by 500 locations, and that is true here as well as it is true here. So, there is no difference will be there even if the program is loaded from a different address compared to the 0 address. So, this helps in something called program relocation. This relative jump, so this helps in the process called program relocation, that is the program may be loaded from a different address, next time it is loaded into the memory. So, that is how these relative jumps are going to be useful. So, these processors they have got these relative jumps introduced, so that we can do this relocation jobs easily. Like when you are thinking about any complex system, then we have to have this many user programs loaded into memory, and it is not possible to ensure that always the program will be loaded from the same address. So, this relative jump will be like this. So, this is say it is an 11 bit sorry, this is an SJMP instruction, SJMP and then the address where you want to jump. So, this SJMP is structure is opcode followed by this relative address, and this relative address is in the range of -128 to +127. So, you can jump by within 256 locations from the current location. So, you can go back maximum 128 bytes and you can come forward at most 127 bytes. So, if you have the machine code is 80 for this SJMP, and then this relative address may be -2. So, -2 is coded as FE. So, this if here is actually if you look into this instruction, the coding of this SJMP here. So, this SJMP here instruction. So, this is a 2 byte instruction. So, if the address if this instruction is at location 1000, then this location 1000 will have the code for the opcode part. So, this is the opcode part, and the location 1001 will have the this relative address part, the second part. So, first one is this one, second byte is this one. So, the next instruction, so if you look into the memory, at location 1000 you have got the first byte OP, at the location 1001 you have got the second byte this value. Now, after that the PC value becomes 1002. Now, after when this instruction has been fetched by the processor, so the PC value is equal to 1002. So, from there we want to go back to SJMP here, and here is 1000. So, from 1002 we want to go back to 1000. So, we need to go back by 2 locations. So, this relative address becomes equal to -2. So, while coding it, so the first byte will be the code for this SJMP 80, and the second byte will be -2. So, that when this instruction is executed with the current PC value is 1002, with that this -2 will be added and it will be going to location 1000. So, that is why, so this is the coding of this SJMP here, this instruction will be 80FE and the FE value equal to -2. Similarly, we can have some other absolute addressing. So, we will see that absolute addressing there SJMP, there AJMP and LJMP type of instructions that we will see later.